Good afternoon once again. In the first part of this lecture series, I presented our work on the pre-treatment of wood biomass for methane fermentation. Now I hope you appreciated the significance of such line of research in alleviating the world's increased dependence on fossil energy. As future chemical engineers, you are tasked to search for cost-effective approaches to translate any basic research into something that could be useful to daily life activities. Who knows, maybe one of you later would put up a company that could transform into reality what we have started in this ChE process. Now, as additional motivation for that person, I would like to add briefly some other unique and interesting applications of ChE. Now, as what I have emphasized in my first lecture, ChE is one of the few available mild approaches for wood pretreatment. It only uses water, enzyme, and energy for ultrafine milling or grinding to release the sugars from wood. The fact that it does not generate toxic compounds during treatment means that it is not only environmental friendly, but it could also be used for feed or even for food applications. For instance, the sugar solution that is extracted from the wood slurry can be converted into a special sweetener through a very simple downstream processing. Now, with traces of wood flavoring compounds, it could even have the same qualities of, say, a maple syrup with some value-added properties. Or you can ferment the sugar-rich slurry to produce food-grade products such as alcohol, vinegar, lactic acid, etc. Now, in fact, we have actually tried one of these. Since most members of our research group like drinking a lot, one of our frequent night outs have inspired us to make the world's first aromatic distilled liquor from wood. Now, the natural flavor of a particular tree species is retained in the distilled liquor. So you don't need to age them in wood barrels since they acquire the essential wood components during distillation. So in 2018, our wood liquor research was released to the Japanese media, and it generated quite some interest, even in other countries. I hope we can try this out in the Philippines as well, using some of our endemic trees. Imagine yourself resting under our national tree while drinking another flavored wood liquor. So truly, our country is blessed with a variety of wood species, many of them currently without any economic value. Now, ChE could open up the utilization of such species for very unique applications. But before you get the urge to leave your seats for a shot of beer or wine, I now would like to proceed on to my main agenda for today. In this second part of my lecture, I will be focusing on an entirely different research theme. This, however, is closer to my early works in the area of wastewater treatment. So here I would address both aspects of heavy metal and organics waste removal used in an actual high-strength waste solution. Specifically, I would like to discuss the Fenton-based treatment of an electroless copper plating waste for organics mineralization and copper oxide recovery. So by the end of this lecture, you are expected to learn the following. Number one, the principle of electroless plating, what it is. Number two, the nature of electroless copper plating solution. Number three, the general mechanism of Fenton oxidation process. 4, the application of copper Fenton oxidation for used electroless copper plating solution. And the cost reduction approach for the copper Fenton treatment process will also be discussed towards the end. Now, in addition to the above, I also would like to mention that my main purpose is not on presenting the actual treatment process itself, but hopefully to provide a glimpse on how to best approach a particular problem from the point of view of a chemical engineer in order to come up with a cost-effective solution. Now let me first define what an electroless plating is. It is a chemical process that deposits an even layer of metal on the surface of a solid substrate, like metal or plastic. This basically has the same purpose as electroplating, but without the use of an electric current. Here, the process relies on redox chemical reactions to plate one surface with the target metal. Of course, the goal is to provide protection against wear and tear, as well as corrosion problems. Currently, electroless plating is an important component of PCB manufacturing in semiconductor industries. During electroless plating, the material to be plated is simply dipped or submerged in a water solution containing the metal salt, such as copper, and the reducing agent, such as formaldehyde. Now, a chelating agent, like tartaric acid, is also present to stabilize the copper concentration, since the solution is generally basic at around pH 10. So without the tartaric acid, the cupric ion would readily precipitate as hydroxide compound at this high pH. Again, electroless plating does not use an electric current, hence the term electroless. So metal coating is achieved by purely chemical means through an autocatalytic reaction indicated as follows. Formaldehyde reduces cupric ions to generate the zero-valent copper metal onto the surface of you want to be plated. Now the first reaction is the oxidation process, while the second one is the reduction process. Electroplating has some advantages over electroplating, such as its ability to create an even layer of metal regardless of the geometry of the surface. Also, it can be applied or it can be used to plate a non-conductive surface, such as plastics. Now, during plating, the copper ion and formaldehyde components are usually replenished when they are used up by the reaction. Up to some point, replenishing these components is okay. However, when the solution is reused many times, the plating efficiency gradually deteriorates due to the accumulation of byproducts such as formic acid. So this leads to its eventual disposal. Now, the used plating waste still contains a high concentration of copper, which is a very toxic heavy metal. Organic compounds such as tartaric acid, formaldehyde, and formic acid are also present in large amounts. High-strength wastes are strictly monitored by environmental agencies, so this requires proper disposal. The following table shows the composition of an actual electroless plating or electroless copper plating solution. The concentration of copper is around 29 millimoles per liter. So this corresponds to approximately 1,900 milligrams per liter or milligrams per liter or ppm. Now the treatment standard for copper is generally below, I think, 0.5 milligrams per liter. Aside from copper, formaldehyde, tartaric acid, and formic acid also contributes to the extremely high COD and TOC loading of the waste. As we know, the discharge limit for COD is around approximately 100 milligrams per liter. So imagine how much of these inorganic and organic contaminants have to be removed for them to be suitable for disposal. One of the simplest and most reliable methods to remove heavy metals is through precipitation at alkaline pH. Unfortunately, the formation of hydroxide flux is inhibited in this case by the highly stable cupric tartaric acid complex. As I mentioned, the pH of the plating solution is already basic to start with. Normally, copper hydroxide precipitates above pH 8, but for the plating waste, even raising its pH to around 12 does not precipitate the copper ions. So for this purpose, it is necessary to destroy the complexing agent to free the cupric ion for easy removal as hydroxide flux. Now, depending on the extent of organics decomposition, this approach would also have the additional benefit of decreasing the COD or TOC of the waste. Advanced oxidation processes such as Fenton reaction is a popular approach for organics removal. Now, classical Fenton is based on the generation of strong hydroxyl radicals from the reaction of ferrous and hydrogen peroxide. The combined presence of ferrous and hydrogen peroxide will initiate the following sequence of reactions. The Fe ions are the catalyst for the system since they are not consumed but simply being transformed reversibly from ferrous to ferric and vice versa. The net reaction is the generation of hydroxyl and perhydroxyl radicals. The hydroxyl radical is considered very reactive. It is able to decompose various organic compounds, generating CO2 gas in the process. The Fenton reaction can therefore be exploited to destroy the copper tartarate complex, thus freeing the copper ion for easy removal with alkali. However, with classical Fenton, you need to add ferrous ion to the system. Now, adding an external metal would generate more sludge during alkaline treatment. Not only that, you now have a mixture of copper and iron hydroxides in the sludge, and this would complicate the succeeding post-treatment stages. Now, chemical engineers generally want to keep things as simple and cheap as possible. So there must be a better way to this. Other transition metals such as copper have been reported to be capable of initiating Fenton-like reactions. Copper Fenton generates hydroxyl species through the following reactions. Now, in this research, we have capitalized on these reactions to treat an actual electroless copper plating solution. As a novel advancement, we explored the feasibility of directly utilizing the copper ions that is already present in the waste. Now, if successful, this would surely cost less and with minimal sludge generation. Before proceeding on with the treatment of an actual wastewater, we first evaluated the copper Fenton of its individual components. So during these runs, we used model solutions of tartaric acid, formaldehyde, and formic acid. The procedure was quite straightforward. You simply add hydrogen peroxide to the solutions and then analyze whether they are removed. Now, the following slide shows the results for tartaric acid. During treatment, we observed a highly exothermic reaction. The temperature increased up to 45 degrees Celsius. there was drastic bubble formation, well, which is a sign of gas being generated. Of course, we were quite excited about these observations since these are good indications that the chemical reaction is going on. So from our chemical analysis, we were able to confirm the very rapid and substantial disappearance of tartaric acid with time. As you can see in the graph, less than 5 minutes was required to achieve maximum removal of tartaric acid, represented by the diamond curve. So from this data, close to 90% TOC removal was achieved. The oxidation of tartaric acid produced CO2 gas, and the remaining byproduct was found to be oxalic acid, which appears to be recalcitrant or very stable to further degradation. Now the following slide shows our data for formaldehyde. Unfortunately, we were not able to see any signs of chemical reaction during treatment. The graphs remained flat, meaning the formaldehyde concentration did not change with time. Now, this initial negative result did not deter us from proceeding further until we were able to come up with better results. A chemical engineer does not give up easily. You simply need to consult your wide arsenal of chemical and physical knowledge in order to find the best solution. As our next step, we performed the same experiment for formaldehyde, but this time at a high temperature. As I mentioned above, copper Fenton of tartaric acid releases considerable heat, so that the resulting high temperature from tartaric acid may have a positive effect on formaldehyde oxidation when they are combined in the waste. So in this regard, we have learned that modified Fenton systems, such as the wet peroxide oxidation, relies on high temperature conditions for effective treatment. However, the temperature should not go beyond 60 degrees Celsius, since at this condition, the hydrogen peroxide already starts to deteriorate. Fortunately, this time around, the copper Fenton oxidation of formaldehyde at high temperature generated a positive result. When we preheated the solution to around 50 degrees Celsius and then added hydrogen peroxide, almost close to 100% removal of formaldehyde was achieved. The formic acid did not form, and TOC was almost close to zero at the end. Now, similar to the above trend, we also did not get positive removal of formic acid at ambient temperature, but we already knew that once we conduct the Fenton reaction at 50 degrees Celsius, then complete removals of formic acid and TOC will be achieved. And that is what indeed happened. Close to 100% removal of formic acid and TOC was achieved at this condition, that is at high temperature condition of Fenton reaction. Now, encouraged by the above results, we finally performed the copper Fenton oxidation of an actual electroless plating solution. So for this experiment, around 2040 millimoles per liter of hydrogen peroxide was added. Now, this value was based on the initial COD of the system. As you can see from the picture, upon the addition of hydrogen peroxide, we observed extensive gas formation, which we knew was due to the tartaric acid decomposition. Now, the temperature increased tremendously, even reaching more than 60 degrees Celsius with one-time addition of hydrogen peroxide. Now, since a temperature higher than 60 degrees is not good for the system, We decided to add hydrogen peroxide stage-wise in small amounts so that the temperature will not breach the 60 °C mark. The following graph shows the removal trend for different organic compounds. All the graphs show a declining trend. Close to 100% removals of tartaric acid, formaldehyde, and formic acid were achieved. These were similarly reflected by the close to 99% removals of COD and TOC. Clearly, copper Fenton oxidation is an effective approach to destroy organic compounds in the electroless plating waste. At this condition, the treated solution can now safely pass discharge standards for organics. But the next question is, what about the inorganic copper ion in the solution? Well, as expected, once the tartaric acid was removed, copper can be easily precipitated during alkaline treatment. However, we were quite surprised to come up with a different type of copper sludge. We were expecting the formation of a bluish precipitate of copper hydroxide, but this was not the case. When we increased the pH of the solution, while its temperature was still high, a black precipitate formed. Now, to fully understand what has happened, we subjected the sample to X-ray analysis and found that it was 30 to 50% cupric oxide. We thought the high temperature reaction was the driving force for the formation of this compound. To some extent, the generation of cupric oxide is advantageous since it has a higher commercial value than cupric hydroxide. Now, the copper oxide also has better flux properties. As you can see from this picture, for the same concentration of copper ion, its oxide flux has 5 times lower sludge volume than its hydroxide flux. Now, this may be attributed to its relatively drier or lower water content. At this point, I would like to summarize what we have accomplished so far. Number 1, we have successfully applied copper Fenton to remove the organic components of an electroless copper plating waste. Number 2, the naturally present copper ions was directly utilized as catalyst, which is very economical. Number 3, with the destruction of the tartarate copper complex, complete copper removal by simple alkaline precipitation was easy. And the exothermic nature of tartaric degradation resulted to the complete disappearance or removal of formaldehyde and formic acid, as well as the formation of copper oxide during its removal by alkali. Now, one would think that we would already be satisfied with our very straightforward and simple treatment approach. We have saved considerable cost from the use of copper catalyst that is already present in the solution. We were also able to generate a valuable copper oxide during hydroxide precipitation, and of course using heat that was naturally generated by the process. However, a chemical engineer does not get satisfied quite easily, especially with regards to many matters. You always try to bring down costs. We therefore asked ourselves if it is possible to reduce the hydrogen peroxide consumption, since it is the major source of cost in the process. To find out, we explored many ways of removing the organic components using alternative chemical reactions. Fortunately, a chemical engineer is blessed to have such deep chemical knowledge to rely upon. Now, from our extensive evaluations, we were fortunate to establish the following. Number one, formaldehyde and copper ions can undergo oxidation reaction at high temperature. And number two, tartaric acid and copper ions can precipitate at acidic pH of around pH 3. So equipped with this interesting phenomena, we modified the overall treatment process by incorporating two pre-treatment stages prior to the Fenton treatment. So as a first pre-treatment stage, we heated the plating solution up to 75 degrees Celsius. And during this stage, red flocks representing elemental copper were formed as the cupric ions were reduced by formaldehyde. Now this process not only removes the formaldehyde but also generates elemental copper, which has an even higher commercial value. Next, we added acidic copper solution to the above pre-treated solution to remove the tartaric acid by forming copper tartrate precipitate. Now you might ask, where do we get such a solution? Well, fortunately, we did our homework and found that the Electroless Plating Company, which is actually a semiconductor factory, generates a soft etching waste that is basically a concentrated acidic copper solution. It was a perfect approach of using waste to treat another waste. In this case, however, it was just another pretreatment. This only removes tartaric acid. By the way, the soft etching waste was added in excess so that the tartaric acid will be completely removed, but still leaving some amount of copper ions for the final Fenton stage. Now this table shows the chemical analysis of the electrolysis plating waste that was subjected to the above pre-treatment stages. So in stage 1, copper ion was completely removed to elemental copper, which considerably reduced the formaldehyde from around 234 to 17 millimolar. On the other hand, the addition of the copper-rich soft etching solution in stage 2 removed the tartaric acid almost up to 0 millimoles per liter. In effect, these two successive pre-treatments has reduced the COD by almost 62%. Now at this condition, we would obviously need much less amount of hydrogen peroxide for the final copper Fenton process. Indeed, from the results of copper Fenton of the pre-treated waste, we were able to reduce the hydrogen peroxide usage by almost 80%. From the previous hydrogen peroxide consumption of 2040 millimoles per liter, the solution with lower formaldehyde and zero tartaric acid now only required to 400 millimoles per liter hydrogen peroxide. Plus, of course, you are able to generate valuable copper metal and copper tartrate during the process. However, this approach also had some limitations. For one, the treated waste in this case has a higher final formic acid and COD as well as TOC. This process also uses up energy for formaldehyde removal, and the final copper removal would also require heat addition if cupric oxide or copper oxide formation is desired. Note that tartaric acid was removed during precipitation, so now there will be no natural source of heat anymore. At this point, I would like to end my discussion about the electroless plating treatment process. Despite our very interesting findings, this research is still a work in progress. But I really do hope that you have learned that for a particular scientific problem, there will always be many available answers. So do not get satisfied easily with a new technology, no matter how simple and perfect it may seem. There may be some other novel ideas that may have been overlooked during the experimentations. As I've always said, chemical engineers have an intensive knowledge in the basic and applied fields of science and technology. So I suggest you use them very well. So if you're interested in the details of this research, this may be found in the following journal. So that ends my lecture. Thank you very much for listening.